Yep. Good morning, everyone. So yeah, today I'm talking about that, like fast sampling of time-respecting paths in billion-scale networks using GPUs. I'm Ashfaq Salehin. I'm a PhD student of informatics funded by Sussex AI, and my supervisors are Professor Luke Bathos and Professor George Parisis. So we say that our work is multidisciplinary. Whenever we are analyzing faults in microservice systems, or we are analyzing pathogen flows among hospital departments, or we are analyzing subatomic chaos on CERN, we are dealing with temporal networks. Now, in these networks, time is merely just a dimension, but a constraint. So any downstream analysis must rely on the same causal order that the events happened with, and our work makes such analysis fast and scalable. So what are temporal networks and temporal random walks? We all are familiar with graphs that they can be directed or undirected. When we add time as a dimension, it becomes temporal networks. They can be best represented as contact sequences where the x-axis is time and the y-axis are the nodes. When we are dealing with very large graphs, this is not very large anyway, like enumerating through all temporal paths from these networks is computationally intractable. It is NP-complete. So we often rely on sampling random paths while respecting the causal direction, which we refer to as temporal random walks. Now let's see an example of sampling a walk starting from node 10. So here's node 10. From node 10, there are two outgoing edges. We will randomly sample one. We follow that, and we reach to node 25 at timestamp 50. Then from node 25, after timestamp 50, there are three outgoing edges. We will randomly select one, and we land at node 50. And then from node 50, there is only one outgoing edge. We follow that, and we land at node 45. So here the walk ends. So the bias toward picking up an edge while multiple valid edges exists is controlled by temporal bias functions. And these functions control exploration versus recency. There are multiple ones like exponential, linear, and uniform. Now, what are the applications of these temporal random walks? So they are the fundamental building blocks of various network embedding techniques like CTTNE, causal anonymous walks, or neural temporal walks. They are very useful in various downstream applications across domains, from anomaly detection in microservice to epidemiology in healthcare. So they can potentially be used to create better and more expressive embeddings. As an example, we can see a Riemannian manifold embedding. This class of geometric embeddings are created to preserve causality from their very core or very design. But current implementations are strictly applicable for directed acyclic networks or DAGs, and they are not that scalable. So with pairing them with a fast and scalable temporal random walk library, potentially we can generalize them for like a lot of other temporal networks as well. So our aim is to create a fast and scalable temporal random walk engine as a building block for causality preserving temporal embeddings. Now, what are the state of the arts? So most of the high performance walk engines are non-temporal. While there are few ones, the state of the art is CPU bound, and it is not scalable to industrial scale demands. So as example, the state of the art T plus, in their paper, they showed that they could scale up to 1.5 billion edges. While in their paper, they also mentioned that their most optimal configuration gets out of memory much before that. And they use some alternative configuration to show that they work up to 1.5 billion edges. Now, our contribution, we created a GPU native temporal random walk generator. We call it Tempest. So this was created with parallelization in mind. So we can generate millions of walks using thousands of GPU cores in just sub-seconds with this library. For this, we created a causality-aware memory layout just for GPUs. And then we added streaming graph support. We also did a lot of like GPU-specific optimization to make it fast. Comparing to the last image, while T plus fails at 1.5 billion edges, while the optimal one fails much before that, Tempest could scale up to 81 billion dataset. That's 60 times larger than them. and also like in short amount of time than theirs. So how we made this faster? So basically, Tempest is a hardware and algorithm co-design. While like first we created one memory layout. I think it's not showing very clearly. The memory layout to represent temporal networks on GPUs. So on GPUs, we cannot use pointer-based data structures efficiently, like maps or sets. So we rely on flat arrays to store the edges, and then we created two logical views to basically represent different stages of walks. Then we have constant time edge sampling functions, where the original ones require like an enumeration over the temporal neighborhood of a node, with some assumptions, which most of the time holds true. We convert it to a constant time sampling function. Then we added temporal window mechanism. So we don't hold the whole data set in memory. Rather than we process data as streams, and we get rid of data when they are past the size of a temporal window duration defined by delta. And this is tunable by the downstream application. And we also did a lot of like microsystem level optimization to make it fast. So the results, we compare Tempest with a Python-based baseline at the beginning. So the Python-based baseline is like vectorized and using NumPy and all of this. Still, it's 60,000 times slower than Tempest. And with the Python baseline, we could at most generate 100,000 walks. And after that, it never finished. While with Tempest, we could generate 10 million walks in less than 3 seconds. It's very like large data generation in very short amount of time. With that, we could scale to a 81 billion data set that is 10 terabyte in memory, on disk. And our GPU implementation could process the full stream in two hours, basically. And we also did a lot of like downstream machine learning validation on temporal link prediction and fraud detection. And in both of the cases, our results were robust and accurate. Now, while the prior like walk generation libraries are either closed source or they require like complex compilation because these are C++ and CUDA libraries, ours is not only open source, but it is also available as a Python executable. So it's regularly installable like any library. And you can just use it to plug and play. And it supports different Python versions and different CUDA versions. We compile them explicitly for each environments. Future work. So Tempest is very fast. It can convert live edge stream to potentially live walk stream. And the downstream models can benefit from the improved context of temporal works. We can potentially try to do temporal geometric embedding with that, using the combined with the geometric embedding techniques. And we expect to get efficient performance of various downstream tasks like anomaly detection and root cause analysis. Thank you.
Thank you, Ashfaq. Do we have questions? Okay, yeah, good.
Thank you for your talk and nice results. My question is, earlier in the slides, you did talk about the Riemannian manifold, which I believe is more about a hierarchical graph.
Yes.
And the particular question was, what exactly is the limit of that particular approach, such that now in your concluding slide, you are still talking about integrating that same approach again? What was the limit earlier you identified, and why do you still consider it coming back at your conclusion?
So we think that like most of the like industrial scale data sets, like for example, server data or any kind of data, they are causal, and any analysis must like hold causality. One particular example is root cause analysis. So you have to go to the root cause from like leaf nodes, something like that, and this has to be causal. Now, modern approaches, like current approaches, they use like they produce the embedding and they use some random walks later on to go to the root cause. While we believe that if some embedding technique holds causality inside itself, probably we can detect the root causes directly in the latent space. We don't have to do any more processing. But for that, we need to make the like Riemannian manifold or such kind of geometric embeddings scalable and generalizable for all kind of temporal graphs. So I think this library will bridge the gap.
Okay. One more urgent question, then John.
So I think, could you go back one slide to the comparison against the validation?
Or
So can you just explain why there is a difference between the full approach and the streaming approach?
yeah,
Is it
so
because I worry about whether the quality of the random walks is different.
yeah, so to compare with the baselines, we followed two approach. In one version, we loaded the full data set into memory, into RAM at once. Now we cannot do it for like, for example, for these data sets, because for this we needed 10 terabyte RAM, which is not really available. So we used a smaller, but still yet a very large data set. In the full version, we loaded it at once. In the streaming version, we loaded it like chunk by chunk, batch by batch, and we get rid of the older data. Now, we didn't make the ML part much complex for this work. We will do it in the next works. In this one, we just use skipgram. Now, skipgram has some known limitations that it cannot like work with streaming data very well. So for this, we have a 4% performance gap here, but it's very consistent, and it is consistent with the noise injection. So we believe that we can close this with like further modeling, like improvements.
Well, thank you very much.
Thank you.
Last but not least, we have Johanna.